Okay, welcome everyone. Today I'm going to take you into a bit of a deep dive into basically what FaaS platforms, especially FaaS platforms on Kubernetes, do in terms of performance optimizations. And to do this, we have to basically first cover basically what I think is the central trade-off in serverless computing. And basically one side of this trade-off is basically the performance model. And of course, performance is always relative. But there are a number of key terms where we think of when we think of serverless that are benefiting its performance model. So first off, you probably all know about this scaling model of serverless where you defer all your operations to the cloud provider, which in turn basically offers you this complete autoscaling. And of course, unless you go into extreme cases, you have this idea of infinite scalability. Secondly, you also, because your functions are hosted on by a cloud provider, you also sort of expect that the availability level is about the same as other services of this cloud provider. And finally, a bit more controversial point is that also what we now see is that more and more serverless is getting used for more latency sensitive applications. So, and of course, this basically is more, relatively speaking, from the start when AWS first launched, the cold starts were still in the seconds, and now we have already seen in other talks that this cold start has gone down into a couple hundreds of milliseconds, which allows it to be used in more and more latency-sensitive applications. And the other part of this trade-off is basically the cost model, and this is arguably even the better selling point of serverless, which basically everyone is aware, of course, about this, that you don't pay for any idle resources. So you only pay for the actual resources that you use. Next to that, you also don't pay for any operational costs, so any upfront costs or any periodic costs which are unrelated to your usage. And finally, if you do use it, then you do get billed very granularly. So you pay by the milliseconds instead of by the hour or day in other more traditional cloud models. And of course, this is still a trade-off, and service isn't magic. It doesn't give you suddenly supercomputing resources for free. Because there's always there's also a balance to be found. And what is interesting about serverless is that it actually tries to explicitly optimize this performance cost trade-off. And this is basically this question, how they do this and what kind of trade-offs are being made, is basically what I'm going to talk to you about in the remainder of this talk. But first, to get to these optimizations, I first have to give you a bit of a tour, basically what a function as service platform contains. And this is work I did together with a group of researchers and industry participants from Netherlands and Germany. And we found basically this architecture where we found basically a build time in which the developer is creating, managing, manipulating its functions and uploading them to databases, and the runtime. And today we're going to only focus on this runtime, where we focus on executing these functions as fast as possible. So to zoom in a bit, we have we can basically represent the data storage in a function service platform by two abstract data stores. So in the first one, the function metadata store, we actually store all this function metadata, such as the function configuration, no worries, the function configuration, environment variables, versioning, all this stuff. And this contains a pointer to the actual function, which is stored in a separate database called the function store. And in this case, this is a simple Python function. And the reason why there are two stores is basically because the usage patterns are so different. Because we are in our FaaS platform, we're frequently accessing this function metadata. We're frequently looking up basically where the function exists, what kind of function it is. And it's also very small amounts of data. Whereas with the function store, these functions, Python function is of course a very small function, but as you can imagine, that once you start using Java functions, for example, or functions with very large assets, then you suddenly go into tens or hundreds of MBs of data for a single function. And with these two stores, we can basically create like a very minimal FaaS platform. And so in this, a FaaS platform runtime. And so here we can basically see that there are a couple of components that you always need. So for example, a router, which basically is the component which needs to accept incoming events, requests, how you want to call them, and which then can trigger this deployer. And the deployer is basically the component which decides which function and how it should be deployed. And then this decision, how it's deployed, is basically deferred, the actual work for it is generally deferred to a separate resource manager. And in this case, this is obviously Kubernetes. And then finally, basically once Kubernetes has deployed all these resources, what you end up with is a function instance. And this function instance is basically a worker which is capable of executing your function based on the incoming requests. And to give you a bit of a concrete example, here I'm currently working on Fission, and we see this if you remove all the more complex components, you see that this same architecture back also in Fission. So we have this, I have an actual thing called a router which does the same thing. We have this, we have an executor which is sort of similar to the deployer. We store our function metadata in Kubernetes CRDs, so custom resource definitions. And depending on your Kubernetes setup, this generally is an etcd cluster. We depend, of course, fully on Kubernetes, and we have a small service which actually stores these functions. And not only so, and to continue a bit, this architecture also allows us to address the elephant in the room, which is basically a cold start. And a cold start is basically the worst case scenario that your function execution will take through the system. And to illustrate this a bit visually, suppose you have some request coming into the system, the router doesn't know a function instance where it can route it to, so it has to ask the deployer to actually deploy this function. The deployer fetches the function metadata for this function to basically get all this configuration, and based on this configuration, it decides how this function should be deployed. This decision gets converted into instructions, gets sent to the resource manager, which is actually all the grunt work, which also includes fetching the function from the store and deploying this function instance. And only after it's completely deployed can we start to route this request to the function the function instance. And the function instance does the work, sends back the result, and this result is sent back to whoever is waiting for this response if it's a synchronous execution. And to compare this with basically the opposite, which you can call a warm start or a warm execution. And in this case, there's a request coming in. For some reason, there's already a function instance available. And you can immediately route it. Function instance does the work, sends back the result, and you send back the result to whoever is waiting for it. And to put a bit more on this, so it's not only that the basically cold start it's not just that the cold start is just calling a lot of other components. It also differs widely in performance, of course, because the cold start has to first do a service call to this deployer. This deployer has to fetch the function metadata from the etcd cluster, which in the best case takes tens of milliseconds, and in the worst case, hundreds of milliseconds. Then you actually have to start to deploy this function. You have to trigger Kubernetes. Well, if you know about Kubernetes, it's good in many things, but it's not very fast. So, and this also includes fetching the function from the function store. And as we talked about before, if your function is small, it's not a really problem, but if your function gets bigger, this also becomes a significant factor. And then you actually start to deploy this entire function. Only after it's completely ready, you can start to route this request to this function and execute the actual function. And if you compare this, of course, to the warm execution, you simply just route the request immediately to this function instance, and then you can start the execution. So as you can see, the performance differs in this case a lot. And it's not just true for our abstract Kubernetes-based architecture. This is actually true for all FaaS platforms currently. So this is an example of research done last summer, where basically researchers looked basically at the cold starts at the three big providers, AWS, Google, Azure. And they found that basically even at the most production-ready system, so AWS Lambda, they still have about 200 milliseconds of cold start. And that's not to say that they're just were not that good, and that AWS is just not good, well engineered. They basically have already employed a lot of optimizations to actually get to this 200 milliseconds. And basically what they did, or at least what they do and what the other FaaS platforms do, is basically what I'm going to talk to you about in the remainder of this talk. So I'm going to basically review some of the techniques that they use to improve the performance, and also basically at what kind of cost they do this. So the first optimization is function resource reusing. And the idea behind this is basically that we can try to share these function instances between function executions to avoid part of the cold start. And for this, we have to basically take a step back a bit and think about what a function execution is. So in theory, so if you think about function executions in a program or even in Lambda calculus, you really think about these function executions as being completely independent, completely self-contained and unable to influence each other. So if we want to replicate this in a FaaS platform, at its extreme, what we need to do is basically deploy for every single function execution a new function instance to ensure that they are fully isolated from each other. And this, of course, so this is great, of course, if you want to have full isolation. But you can imagine that this basically means that every single function execution gets a cold start. So what the alternative is to start to multiplex your function executions onto a single instance. So basically, you use a single instance to serve multiple requests. And this basically means that only the very first request, which triggers the cold start, and the all others basically can reuse this existing function instance, basically having a warm execution. And that's basically, to get back a bit, that's not to say that the former approach is completely bad, because there might be cases, for example, in mission-critical scenarios where you actually want to have this full isolation. For example, when you're dealing with very privacy-sensitive data or with very performance-critical applications. But what we see in practice, and also what these researchers saw in practice, was basically all these FaaS platforms basically reuse resources in multiple ways. So one way that what they do is basically bin packing your functions onto the same machines. So whereas if you would have expected as a user, basically if you deploy two functions in AWS, that it will be distributed equally across multiple systems. In reality, all your functions get first packed into a single machine, and only after that machine is full, an additional machine gets added. And this is of course great when you because if you have many functions, this means that you have there's less likely that you have influence from other users influencing your functions. So for example, if it's a malicious user. But of course the problem is when all your functions are very CPU intensive, this will likely influence you will likely be influencing the performance of your functions. And on these machines, your functions are still isolated. So they're containerized or using micro VMs to actually ensure that they're functionally isolated. This means that you cannot really access your functions functionally, although you might still be able to influence them in performance. And finally, for a single function instance, you basically do share these function instances between these function executions. So multiple function executions will be using the same function instance, and this could allow a function execution to actually alter the state of the function instance in such a way that it can alter the result of the following executions. And this might be a bad thing, but for example, Google Cloud Functions actually mark this as a feature, where basically they say you can write to this temporary disk on your function instance, and you can basically use that as sort of a caching mechanism for your future function executions. And just to get back to a bit to our initial architecture, to add this function reusing to this, we can add a small cache. So what happens now is basically that a request comes into this router, checks this cache whether a function instance of its correct type is still available, and can immediately forward the function execution to that existing function instance. If it's not available, then we still have to go through this deployment, this entire cold start. And of course, there's also a question, there's a trade-off here, because how long do you want to keep these functions alive after you've used them? Because you can keep them alive for an infinite amount of time, or for weeks on end, and this basically means that your function executions in the future will likely be able to reuse this existing function instance. But of course, the downside of this approach would be that you're keeping these function instances alive for very long times, incurring cost, without actually having been guaranteed that there will be function executions coming in. So you can take a more cost-effective approach here by setting these keep alives very short. So keeping them only alive for a couple of seconds, or a couple of milliseconds, a couple of minutes. And this basically means that you're saving a lot of cost, but the problem here is, of course, that there are many other function executions in the future that might actually not be able to reuse these function instances and have to go through the entire cold start, just because these functions weren't kept alive for long enough. And these researchers, which I mentioned earlier, also looked into this question, basically about how long do the major cloud providers keep their functions alive. And they found that basically they opt far more for the former approach. So they go for at least several hours or several days for keeping the function on average alive on average. So, and not only can we start to try to share these resources after functions have executed, we can also try to share them before they actually get executed. And we do this with an optimization called function runtime pooling. And to get to this optimization, we have first to understand basically a couple of key insights. And one of them is that basically a function instance, this worker which can execute functions, is basically composed of two parts. So one part is your function-specific code, and one part is so this function-specific code is basically your Python function which you've uploaded as the function. And then there's the runtime, which is basically all the operational logic surrounding your function, such as health checks, such as monitoring, such as deployment hooks. And basically, this runtime is generic, so it means that basically it is not relevant. It's not specific to any kind of function, so it can be used for any function, regardless of its language or type. And with this insight, we can also divide this deployment process into two steps. So we can divide this deployment process into the first deployment, where we first deploy a generic runtime, and which in some FaaS platforms is called a unspecialized runtime, unspecialized function, or a stem cell. And then in the second step of this deployment, we can start to deploy this function on top of this generic runtime. So, and then thereby actually specializing it. And so with these two insights, what we can actually do is something called resource pooling. And I'm guessing that you're all familiar with resource pooling in some way, but just to give an example, in many applications you have these thread pools in which you want to avoid the expensive creation of threads basically in your critical path, so you create them ahead of time, put them into a pool, and basically take them out and use them once you need a thread. And in Serverless, it's not much different. What we can do, for example, is we can create a pool of free generic runtimes ahead of time. And then once at some point we actually need this, to deploy some functions, we can take these generic runtimes out of this pool and only do the last step of this deployment process to deploy the function on top of the runtime. And we basically reduce our cold start with this. And asynchronous to this, basically this function execution, we can then start to rebalance this pool, adding runtimes until it's basically again at the desired size. And to reflect this a bit on our architecture, in our architecture, we can reflect this by adding these two components. So one is basically that we reflect basically that the function instance always has some sort of a function runtime around it, which is more generic. And we can add a component called a resource pool, or in Fission we call this a pool manager, which basically is a component that's responsible for balancing or keeping this pool at the correct size. adding runtimes if needed. And of course, here again, the question is why did I choose this number 3 for this run pool? And it's of course an arbitrary number. Because this number really affects both your performance and your cost in some way. So we can go for a more performance-aggressive side, basically choosing to go for a very large pool of tens or hundreds of these generic runtimes. And with this, we ensure that there's really that we can handle like even very spiky workloads, which basically have high concurrency, which need to deploy a lot of function instances at the same time. And again, the problem here is, of course, that this pool is not something is not for something very serverless, because it's there around, it's being kept alive at all times. So that means that you're also incurring costs at all times, which basically is added to the overall overhead of a FaaS platform. So the opposite side of this is basically that you go for minimal pool, so where you have a couple of runtimes or no runtimes at all in your pool. And this, of course, saves you a lot of cost. But the problem here is that you lead to something called pool exhaustion, where a workload with more than expected workload, so with a bit more spikiness in its concurrency, arrives, and it fully exhausts your pool of runtime. So it takes all your runtimes out of your pool, and then afterwards, functions that need to be deployed have to go through this entire cold start, because they now also have to wait to deploy these runtimes, and then this function instance. So, and not only can we actually prepare these runtimes ahead of time, we can also prepare a bit more the functions themselves ahead of time with something called function prefetching. And so the idea of function prefetching, to be a bit more specific, is that we try to fetch these function sources proactively, so ahead of time, and place them near or in the runtimes that might need them in the future. And the idea behind this is that we basically want to avoid incurring a lot of this function transfer latency, because as we discussed earlier, the functions might become tens or hundreds of MBs of data, which quickly makes your data transfer latency a significant factor in your cold start. And you can imagine that this problem of basically this function latency, this transfer latency, only increases in severity when you're trying to deploy your FaaS function on a geo-distributed way, so across data centers, or on an edge computing way. So basically, where you suddenly also have to transfer these function sources from one data center to the other. And you can think a bit about this optimization as being basically a hierarchy of caches. So at the far top, we have this remote storage, where we basically store these functions, and which basically acts as the function store, which is the source of truth. And below this, we have multiple layers of caching opportunities. So layers where we can cache our functions in or near the runtime. So we can choose to cache them at the cluster level, machine level, or even in the most extreme case, we can already basically preload them into these generic runtimes ahead of time. And this, of course, again, is basically a bit of a trade-off. Where do you actually place? Where do you place these functions, and how many do you place? Because in the ideal world, where you have infinite amount of storage, and basically it's all free, you obviously would place all your functions everywhere throughout the system, and especially at the function level, you would place them at every single runtime. Downside is, of course, that we're not living in an ideal world, and storage does cost money, and also storage is not infinite, so there will always be limits at how much you can store, how much you can cache of these functions. So then, in that case, you can basically also take a more cost-conservative approach, basically being more selective about where you cache your functions, caching them only at very specific cluster levels, for example. Or in extreme case, you cannot cache anything at all. And there you simply rely on this single remote storage. And this, in this case, basically in the last case, that's of course a bit of a performance issue. It will come because if you depend on, for example, some FaaS platforms also depend highly on, for example, Docker Hub to actually deploy their functions. that's basically getting, if you know about Docker Hub, then it's probably, it's not very fast in actually getting your images. So if you depend fully on this single mode of storage, it will likely impact your performance. And to give you a bit of an example, it might be a bit silly, but just to give you a bit of illustration where it would fit in this architecture, we just placed this cache in front of this function store just to indicate that likely the deployer will never actually interact with this function store, this remote function store. And instead it will use some cache. And so this brings us already to the last optimization, which is called function prewarming. And the idea of function prewarming is basically that you can try to avoid, you want to try to avoid these cold starts in their entirety. And to be a bit more specific, the idea of function prewarming is basically that you try to anticipate these function executions by preemptively deploying function instances. So basically deploying them ahead of time, expecting a certain workload to come in for them. And this idea is not new. It's basically, I think it's known mostly as being predictive scheduling in many domains. So for example, you have this in the CPU of this branch predictor, which currently is a bit infamous. But the idea of the CPU branch predictor is also that you have this code with multiple branches, and basically this branch predictor tries to predict which branch your program will take. And based on that prediction, it will actually do some preloading of the registers. And the same thing goes for proactive outscalers, which basically are mostly in research. But the idea of proactive outscalers is basically that they try to predict the future load on your application, on your VMs, on your containers, and will scale them ahead of time to that expected workload. And finally, we have these predictive caches, which actually load themselves ahead of time with keys which I expect that users will request in the near future. Just give you a bit of a visual, idea of how this looks like. Without prewarming, we have this very simple graph where on red we have the number of function instances needed to actually serve this workload that's coming in, and in blue we have the actual function instances deployed that can actually handle this workload. And you see at T4 we have some workload coming in, which requires the deployment of function instances. And only then at T4 we can actually start to deploy our function instances in a case where we have no prewarming. And no matter how small you make your cold start, how much you apply these optimizations we talked about before, you always, in many cases, you still have some form of cold start. So it contrasts this with basically the ideal case of prewarming, where we have basically somehow we know exactly by perfect prediction that at T4 we have this workload coming in. And this allows us to do some pre-warming by basically deploying the functions ahead of time. So at T2 we start deploying, at T3 they're ready to actually handle this workload, and at immediate T4 we can start handling this workload. And as you see the difference in the top figure, basically the difference between T4 and T5 is basically the time that it's the cold start. And in the lower diagram we don't have this cold start. But as you can imagine, basically predicting anything, so also predicting function executions, is difficult. It's also an active field of research in many of these other domains that I talked about, so especially in proactive outscaling and in predictive caching. But in general, what we find is basically that in all these domains, and also in the early stages of pre-warming in serverless, we have two types of approaches which we can take to actually do these predictions. We can do runtime analysis, so basically having some component constantly monitoring your functions and basically collecting all kinds of interesting data about this. So basically how long did the function execute, how long did it take to deploy, what's the pattern of the incoming workload to these functions, what's basically the size of this workload. And basically based on this data we can use some technique to actually turn this data into a meaningful model which we can use to generate these predictions about the future. And there are many techniques for this, and so from simple rule-based techniques to very complex pattern recognition. And I hope you understand that this is another this is a subject for another hour of talk to actually dive deeper into this. So I'm going to leave this for now. And so the next approach is basically more static analysis. So you use the information that you have as a FaaS platform about these functions. And there's also, like with runtime analysis, something that the serverless platform really shines in, because you have so much, as a platform, you have so much information about your functions. Basically, because you deploy this, you control this entire life cycle of this function. You control how to deploy it, you control how it's monitored, how you control how the events or the requests come to the function, when, and so forth. And based on this information, you can also create some very meaningful models. And so, for example, to give you a bit of idea, what you could do is actually provide some dependency knowledge. So you might know that, for example, function A will always be called after function B, or you might know that the user has set up some trigger to basically trigger an execution of your function every hour, every day. But predicting is not only hard; it's also, again, a trade-off. Because, as you can imagine, a prediction is never a certainty. It's always the predictor has to attach some threshold value to this. Basically, how certain it is of this prediction that there actually will be a function instance needed. And we can be very optimistic about this. Basically, setting this threshold for believing these predictions to be very low, which basically means that even at the slightest hint of that a function instance will be needed, we're already preemptively start to deploy this function instance, basically pre-warming it. And this is, of course, great for your performance, because the sheer likelihood that your function instance will be pre-warmed is larger. But of course, the downside is here that you will get a lot of misprediction, get a lot of false positives. But if basically predictions, or basically where you pre-warm your functions based on predictions of workloads that never actually arrive. So in that case, basically you have deployed these function instances. You have pre-warmed them, but you're not actually using them. So basically, you've wasted resources. And to give you a bit of an example of this optimistic pre-warming, we have to go back a bit to the beginnings of serverless or FaaS platforms. So when AWS Lambda was first released, we had this. People started to find out about these cold starts, and they were back then far worse than they are now. So they were still in a couple of seconds for AWS. And what people wanted to try to avoid these cold starts, and what they thought about was basically doing some sort of a ping hack, or basically warming your functions periodically. And what you did, or what you still do, is basically set up a cron job or a service which regularly pings your function every 5 or 10 minutes. And this basically allows you to pre-warm your function and basically keeping it warm at all times. And of course, this is a bit of a simple hack, and it's also a bit silly because it only works for one function instance and not for many. So if you still have a spiky workload coming into your system, you still have not enough function instance pre-warmed. But I think it's a good example of what basically very optimistic pre-warming is about. And just to get back to this trade-off, we can also go to the other side, of course, being far more pessimistic about our pre-warming. So we can say basically we only believe this prediction to be that we only believe that this prediction is true when it meets a certain threshold in confidence. So in that case, only when we're absolutely certain that the function execution basically that the workload is coming in for a function instance, then we actually start to act on this and pre-warm the function instance. And of course, the benefits and downsides here are sort of reversed, because you now ensure that you no longer really waste many resources on these mispredictions where you pre-warmed useless function instances. But the downside is, of course, that you also miss a lot of opportunity to actually pre-warm function instances, because you just set this threshold so high, and if you only had to set this threshold lower, then you would have been able to pre-warm them, and they would have benefited from being able to execute warm instead of having to go through a cold start. And to give you a bit of an example of pessimistic pre-warming, I have to take a quick detour to introduce you to a system I've been working on for last year, which is called Fission Workflows. And Fission Workflows is basically a system which allows you to compose smaller functions together into basically far larger complex function compositions, which we call workflows. And the idea behind this is basically that you as a user don't want to recreate your functions from scratch every time you have a different use case. Instead, you want to glue together existing functions into different configurations. And in contrast to basically doing this yourself, by calling, for example, functions from other functions, a workflow engine gives you a lot for free. So it gives you, for example, it abstracts away a lot of the complexity of basically transferring data and control signals from one function to the other, while also giving you basically monitoring for free and some fault tolerance mechanisms at a reasonably low overhead. To give you an example, here we have a small workflow where at one side an image is coming into this workflow. It first gets validated, then this workflow branches off into a parallel execution of two functions. So in the lower one, we resize this image, basically resizing this image, and in the top branch we have a sequential execution where we first run an image recognizer on this image, and then translate this text into a different language. And then finally we have this function which basically synchronizes these two branches and combines this resized image with this translated text. So, and the reason why I introduced you to Fission Workflows is basically because the idea of this workflow is extremely interesting because it's basically a dependency graph of functions. So you know exactly here that the function on the right will always be executed, or most certainly will be executed, right after the left functions have completed. So to illustrate you this, in this case we have experimented basically with this kind of pre-warming idea with workflows, and there are many strategies you can use, but we have come up with a couple of strategies. And one of them, which one is the first one and one of the simplest ones we come up with, was basically horizon-based pre-warming. And the idea of horizon-based pre-warming is basically that the rule is basically that you pre-warm all functions in this workflow, which depend only on functions that have started or have completed executing. Now this works basically when we have this workflow. It starts. There might be a cold start here. So the first function starts, and then we can basically pre-warm all the next functions. And these functions get pre-warmed, the first function finishes, and that basically means that we can execute the next three functions because they all solely depend on this first function. They start, and they probably have benefited from this pre-warming, and this in turn allows us to pre-warm the next two tasks. And note, we don't pre-warm the last function, because it's still depending on functions that have not yet started or have been completed. So then these next three functions finish. We can start these two functions, and we can finally pre-warm the last function. And so once these two finish, then we can execute. We can start and finish this last function. And of course, this is a very simple example. There are many edge cases to this way of pre-warming. But I hope I've given you a bit of an idea of how powerful this combination of workflows with pre-warming is. So, and to basically complete our architecture a bit, I've included this workflow engine as basically being a small box here. And of course, a workflow engine itself, if you've worked with a workflow engine, then you know how it's a complex piece of software. But just for the sake of screen size, I added here as a single box because the important thing here is that there is an additional arrow going into this deployer. And this basically signals that basically the deployer is no longer solely relying on the router to actually start deploying these functions. So because now instead it can also start to deploy functions asynchronously from the router. So this brings us to the end of this talk. Just to summarize, we've seen 4 techniques that are key to performance in serverless. We've seen that basically all FaaS platforms do some form of function resource reusing. basically trading in isolation for better performance, by basically avoiding parts of the cold start. We've seen that basically with this idea of that we can decompose this function instance into a function-specific part and a generic runtime. We can actually also decompose this deployment into two stages, so in the deployment of a runtime and in a function. And basically, based on these two insights, we can do something called resource pooling, basically pooling these runtimes and basically avoiding having to deploy this runtime in the critical path. And next to that, we have also seen that we can prefetch these functions, basically placing them near or in the runtimes that might need them to reduce this function this data transfer latency. And finally, you can see we can even avoid these cold starts in their entirety by utilizing some form of function prewarming, where we try to preemptively deploy function instances to anticipate future workloads. And of course, these are by far not the only optimizations that are being made in serverless platforms. But what I do think that these four give a very clear picture of what the kinds of optimizations that we're dealing with in serverless. And I think these four also show very clearly how they're basically dealing with obstacles to performance that are very specific to serverless, and also how they leverage the serverless model to actually get to these optimizations. And finally, I think a key thing here is that each of these four shows very clearly how these trade-offs between performance, basically these decisions on these trade-offs between cost and performance happen at every turn of the road. And this also raises an interesting difference between managed FaaS platforms, so managed closed source FaaS platforms, and open source FaaS platforms. So in a managed FaaS platform, such as AWS Lambda, you cannot really configure these trade-offs yourself. You're basically stuck with whatever AWS has chosen for you. And this might of course make sense if you're building the generic service application which AWS had in mind when they were actually benchmarking their products for AWS Lambda. But in other cases, you might actually get affected by this because, for example, you might be overpaying for your AWS Lambda. For example, you have this application where you don't really care about performance. You are completely fine with having it get a cold start of multiple seconds, or that it's not available at all times. But still, in that case, you're still paying for all this, basically for all this performance that AWS Lambda provides to you. And also the opposite case is also still true. You might actually have this application where you would be perfectly willing to pay much more for your functions if only there was a better SLA or better availability guarantees or better isolation guarantees. And in both these cases, you're basically out of luck in the current situation. And I hope and I expect that AWS and other major cloud providers will move towards more configurable options, so basically allowing you to configure more of these trade-offs. But for now, this raises a very interesting difference or benefit for open source FaaS platforms. So an open source FaaS platform such as Fission does allow you to basically configure each of these trade-offs yourself, basically having all the freedom to play around with these settings and see basically how you can fit the resource that you use for this function exactly to the level of performance that you need, that your application needs. And this brings us to basically, I think, one of the most interesting points or aspects of service to me, actually, which also is the takeaway message for today. And that's basically that serverless computing is not just about, and shouldn't be about, just paying for the resource that you use, but it should be about paying for the performance that you actually need. And with that, thank you for your attention.